Okay, question 2.92 here. All right. Before that, I'm just gonna put the value for the G for steel. The G for the steel is 0.973 times 10 to the power 11, and the density is 7.83 times 10 to the power. Okay, so okay then. Steel shaft of 0.05 meter diameter and 2 meter length is fixed at one end and carries at the other end of a steel disc of 1 meter diameter and 0.1 meter thickness, as shown in figure 2.14 below. Find the system's natural frequency of torsional vibration. So the question wants you to find the KT, torsional stiffness, torsional, omega n for torsional. So in order for you to do that, we know that in order for us to find the omega n, right? Omega n will be set K over M, right? But then the question asks us to find the omega n for torsional vibration. So we have to use KT for torsional stiffness. And instead of M, we have to use J. Why J? Because it is torsional. It is rotational motion, right? But for translational motion, we use M. But for rotational motion, we use J naught, right? So we have to use J naught. So we have to find KT and J naught first. Okay, we have to find KT and J naught first, then substitute inside this formula, and then you get your omega n. So let's try, let's do and find the KT for shaft first. Okay, for the shaft, it's 0.05 meter diameter and 2 meter length. So zero point 0.05 and 2 meter length. And then the diameter for the disc is 1 meter. And the height thickness is 0.1 meter. Okay. Now let's try and do this question. Okay, first step is, do it small over here. First step, find the inner shaft. Okay, why? Because the formula for KT for shaft is G. We've already done the question for shaft before. You can refer back to the previous module that I've sent. Okay, so, the solution before. Formula for shaft is KT. For shaft is G times the initial moment of inertia over length, right? So we have to find the I. And I for shaft is $32. Okay, then you just substitute. Okay, this is the disc and this is the shaft. So we have to find for the shaft first. The D for the shaft is 0.05 meter. Divided by 32. So your I, you'll get 6.1359 times 10 to the power of negative 7 meter power 4. Okay, that's your I. And only then we substitute in the KT formula, which is GI over L. So KT is, substitute the value, the G for steel is 0.93 times 10 to the power of 11. Okay, 793 times 10 to the power of 11. Your I is 6.1359 times 10 to the power of negative 7 divided by the length L. L is 2 meter for shaft. Okay, and then calculate this, you get your torsional stiffness to be 2.4329 times 10 to the power of 4 Newton meter per radian. Okay, normally it's Newton per meter for normal K, all right? And then for KT, torsional stiffness, it's Newton meter per radian, okay? Okay, next. For shaft, since the ones moving, okay, the ones moving is the disc, right? The ones moving is the disc. So the disc is actually acts as a mass, and the shaft acts as a spring, I would say, because once the disc is rotating, okay, the ones having an impact on the ones being twisted when the disc is moving, right, rotating clockwise. Okay, the ones being twisted is the shaft. Okay, the shaft is being twisted when the disc is rotating. So from the shaft itself, we can find the stiffness. Okay, and for the disc, since it's just rotate, it doesn't do anything, so we can find the mass from using the disc. So for shaft, we find the stiffness, and for the disc, we find the mass J. Okay, so now let's do for the disc. Okay, over here, there's going to be a lot of derivation, so please bear for a while for this part. First of all, volume for a disc okay, volume for a disc is pi d squared of 4 times the thickness or the height. Okay, and then for density, the formula is rho equals to the mass divided by the volume, right? Okay, so basically the mass equals to rho times V. Okay, now let's say I want to find a mass. Okay, so the mass will be rho times V, which is your V is this volume for this. Right, so that's your mass for this is the formula for a mass for disk. Okay, then we want to find for J naught. Okay, this formula right here, you can find it inside the textbook, page 176 if you have the textbook with you. Okay, so J naught, okay, basically J naught equals to mass times diameter squared over 8. And then again, you have to further substitute the mass using this formula up here. So your J naught formula will be rho pi d squared h over 4 times d squared over 8. Okay. And then further simplify both d squared. So you'll get your J naught to be rho pi d to the power 4h. and then 8 times 4, you get 32 lah. 32. Okay, so this is the formula for the J0. Okay, and then we already have the value for everything here. So just substitute all the values, then you can get your answer for J0. Let's separate this. Okay, J0 will be the row. Density for steel is 7.83 times 10 to the power of 3. 7.83 times 10 to the power of 3. And then times with pi, times the diameter for the disk is 1 meter. Okay, diameter for the disk is 1 meter. Sorry, 1 to the power of 4, right? Diameter to the power of 4. Okay, and then times the height. The height is 0.1 meter. Divided with 32. Okay, so in the end, your J0 you get as 76.87 kilogram meter square. Okay, this is the value for the J0. And how are we going to get the omega n? K stiffness over mass, right? Square root. So that's the last step. Omega n equals to stiffness, this one here, 2.4329 times 10 to the power 4. Divided by the value for the J0, KT over J0, 76.87. So in the end, your omega n, you get your omega n to be 17.79 radian per second. And that is the answer for this question. So do you guys have anything that you guys want to ask? Before I'm moving on to the next question? No, huh?
Excuse me, sir.
Okay. Yes, yes.
So for torsion, the formula for J will be different from from the transverse.
You mean the transverse motion?
Yeah.
Yes. There's a few of the G0 formula that you can find inside the textbooks based on the question. But for this question here, the J0 equals to the mass times the diameter squared over 8 lah. Based on the steel, based on the disk. The formula for the J0 for the disk. If I'm not mistaken, different shapes have different formula for J0. It's not based on the motion, it's based on the shape, if I'm not mistaken. You can try check it in the textbooks. There's a table for J0. I'm not mistaken lah. But I'll try to find in the textbook the table for the J0 and I'll screenshot it and send in the channel later. Okay?
Okay, thank you, sir.